Right. So, as you approach the coast, well, we're in various different regimes, aren't we? We've talked about deep water. This is deep water. This is shallow water. So when you're in deep water, the wave crests travel at root g over k, speed root g over k. The energy travels at the group speed, which is half the phase speed, right? And that's a simplification. So we're in depths which are greater than about half the wavelength here. Then in the shallow water, in depths less than, well, considerably less than the wavelength. We call that shallow water. And again, we can make this simplification. Phase speed is equal to root gh, and also the group speed at this point is also equal to root gh. So these waves are non-dispersive. The group speed is the same as the phase speed. And then there's this kind of in-between area where you can't really make a very strong approximation one way or the other, so you'll just have to use the full expression for the phase speed. And the group speed will be between these two limits. The group speed, it'll be faster than what happens in shallow water and slower than what happens in deep water. I mean, you can write down the expression if you want for the group speed. You just have to differentiate that. I'll leave that to you. You can't make an approximation here. There's one thing we haven't talked about yet, though, and that is what happens when it gets more and more shallow. Well, the phase speed is a function of the depth, right? So you're going to expect your phase speed to be changing with depth. So let's look at that now. All right, so as we approach the shore in shallow water, getting more and more shallow just right to the shoreline there, the waves must slow down, right? Because c is equal to root gh. G is not going to change. H gets smaller, therefore c gets smaller. The waves will slow down as they arrive in shallower and shallower water, right? Now we know that the speed of the waves is omega over k, or the frequency times the wavelength, if you like. So what's changing? This is a question. What do you reckon? As the speed gets slower and slower, either the frequency has to change, or the wavelength has to change, or maybe both. What do you think? What do you think? Do you think that who thinks the frequency is going to change? Or I'll give you a second to think about it. Either the frequency changes, or the wavelength changes, or maybe both. But something's got to change, because c is equal to f lambda, right? And c is going to get smaller as you approach the beach. This is a motorway, right? This is the autoroute. And then you get to the péage, okay? And well, the autoroute is quite long, you know. And there's cars driving along on the autoroute. They're all being very sensible, because most people drive very sensibly, keeping a decent distance between them, you know. Apart from this guy, he's an arsehole. He's got a BMW, so he's right there. But mostly, you know, they're keeping a sensible distance apart. And what we have here is a policeman. French policeman. He's got a French policeman's hat. And his job is to count how many cars go past every minute, right? And then you have another policeman here at the péage. And so what do we have at the péage? We have cars going past, and they're queuing up to get through the péage. And his job is also to count how many cars go past every minute, right? So let's say that this policeman here counts 50 cars a minute, right? How many cars per minute is he going to count? More than 50? Less than 50? What do you reckon? All right, who thinks more than 50? Yeah, got one. Brave man, brave man. Who thinks less than 50? All right. Oh, most people think it's good. So there's going to be less cars going through here per minute than here, you reckon? So, all right, my question for all you people is, what happened to all these cars then? There was 50 a minute going past here. How many, let's say there's 30 a minute going past here or something, right? There's 20 cars a minute which have disappeared, right? It's like maybe it's true. Maybe there's a flying saucer that comes and picks up cars off the motorway, right? That's what you're saying, right? So what's happening is that these cars are going faster than these cars, right? You have to slow down when you get to the toll booth, right? But, as I very clearly pointed out, they're much further apart as well, right? And they slow down and they group up together, right? So that you have a conservation of cars, right? You have to have the same number of cars. You can't just remove cars or add cars. So the number of cars per minute here is 50. That means the number of cars per minute here, it must also be 50, right? You have to have all the cars that went past here, a few minutes later they'll arrive here, all of them, right? So in a steady state, the same number of cars per minute, which means that basically the frequency is conserved, right? You haven't changed the frequency. What you've done is slowed down and changed the wavelength, right? So you have a long wave arriving at the shore, slowing down and shortening, but the frequency stays the same, right? Remember that. Omega can't change. There's no mechanism whereby you can remove wave crests or add wave crests. So in a steady state, the frequency stays the same, the wavelength changes, and the speed is reduced as it arrives at the beach. One of the consequences of changing the wavelength is that you have another conservation principle, you have conservation of energy, and the total amount of energy stored in one wavelength is proportional to the amplitude squared within that distance. So it's proportional to a squared times lambda, the total energy here. The energy density is proportional to the amplitude squared. The total energy is the amplitude squared times the space that it occupies, one wavelength. A1 squared lambda 1 will be equal to A2 squared lambda 2, where you have A1 squared lambda 1 and A2 squared lambda 2, right? And that's something you can use to calculate how the amplitude of the wave will change. Obviously, as you can see, as I've drawn it, if the wave gets shorter, then to conserve this thing, which is proportional to the energy, the amplitude must increase, right? And this is what happens. You can see it. You saw it on the video I showed at the beginning of the course. You can see that as the waves get closer to the shore, into shallower water, they get bigger. And then if the profile of the depth is just right, the waves will get beautifully big and curving and break, and you can surf on them, right? So that is why the waves get bigger as they approach the shore. It's because, to start with, you have conservation of number of crests per minute, and then you have consequently a shortening of the waves as they arrive at the shore, and conservation of energy means that they will get bigger and break.